Okay, 12.7, we're going to do triple integrals in spherical coordinates. So we're going to kind of build on what we did with the cylindrical. Spherical coordinates are actually rho, not to be confused with density, theta, phi. Okay. Rho is going to be described as the distance from the origin. Now this is different than r in your cylindrical coordinates because this is not just in the xy plane. So when we're talking about cylindrical coordinates, r is in the xy plane and planes that are parallel to the xy plane. Rho is just anywhere in space. That's your distance from the origin. Okay, so not just the xy plane. Okay, theta is your distance, same as it was in cylindrical. Angle measured counterclockwise from the positive x-axis. Okay, so again, that's the same as polar. Okay, and then we get phi. This is the angle measured from the positive z-axis. Okay, now theta will be between 0 and 2 pi. Rho is always positive or 0. Phi is just between 0 and pi. Okay, and that can get us any point that we need then in our three-dimensional coordinate system. And I'm just going to draw a little diagram to go with this. Okay, so in our rectangular coordinates again, okay, we might have an x, y, and let me get that a little bit longer for the y. Okay, so that would kind of be projected that way. And then we would have a z. Okay, and there would be our point. And in fact, we could complete that kind of rectangle. Obviously, why we call it rectangular coordinates. You know, I listened to the playback of one of my videos. I didn't realize how loud that tapping of my pen is in the recording. Anyways, there we go. And I'm actually going to go over these a little bit thicker. Might as well just use a thicker pen, right? And that didn't work. Hold on. It should have worked. Okay, I guess it's kind of working. Why? Hopefully that doesn't look too messy. See. Okay. All right. So now if you want to do the same point using our spherical coordinates, okay, we would have our theta okay, and actually I'm going to do it using a thinner pen right now. And let me just, should have thought about that for a second first. Theta's not really, okay, so there would be our theta. Okay, and then this distance here is rho. So it connects the origin to the point, okay? And then this angle here would be phi, okay? So with only two of those, you wouldn't be able to get there, okay? If we only knew what theta and rho were, we wouldn't know how high to put that point, okay, which is what phi gets you. And if we only had like phi and rho, we wouldn't know what angle to make in the xy plane. So you do need all three of those. So kind of get that straight in your brain there, okay? But that would give us our point, again, rho, theta, phi. Okay, and I'll make that one so it goes along with our other one. A little bit thicker here. Okay. So now we're going to get some of these conversions here. All right, so one thing to think about here, use purple maybe, okay, is that rho, so think about rho sine phi, okay? Rho sine phi would give you this distance here, because that's that right angle that, okay? So rho is the hypotenuse of a right angle. Sine phi would give you opposite. So that's also going to give you this distance down here. Okay, so this piece right here would be rho sine phi. Oops, not theta. Okay, and then so rho cosine phi would actually give you that distance along the z-axis. Okay, so here, this one would also be rho sine phi. This would be rho cosine phi. Okay, and so this would be rho cosine phi. Okay, so there's z, right? We have our conversion for z. Z is rho cosine phi. Okay, now your x, we got to think about that rho sine phi as being a hypotenuse of another right triangle. Okay, so rho sine phi cosine theta will give you x. Okay, so x is rho sine phi cosine theta. Okay, and then your y would be rho sine phi sine theta. Okay. And we can also make the conversions for going from rectangular to spherical. So we can do x squared plus y squared plus z squared would be rho squared. Okay. Theta would be the inverse tangent of y over x, just like it is in polar. Okay. And then phi, okay, would be actually, we do this one as the inverse cosine of z over rho. Okay. So again, phi, if we're looking at phi, adjacent would be here, the cosine of phi would be adjacent, which is rho cosine phi over hypotenuse, which would be rho. Okay, and rho cosine phi is just z. Okay, so that's where that comes from. Seems like a kind of a weird relationship, but it's right there. Okay, so there you go. Okay. So we'll practice plotting some of these. Sorry, I needed some water quick here. Hold on. Okay, so let's practice plotting some of these. So for example, let's do 4 negative pi over 4 pi over 3. This is in spherical, okay? So we're going to plot, and we're also going to convert to rectangular. Okay, and then we'll do another one where we have square root of 3, negative 1, 2 root 3. We're going to plot that and convert it from rectangular to spherical. Okay, so let's get our coordinate planes here. Okay, so the first one, okay, remember this is rho, theta, phi. Okay, so we are going to be on theta at negative pi over 4. Okay, so here's theta. Okay, and then for phi, we're at pi over 3. So remember that's measured from the positive z-axis towards that. Okay, so pi over 3 might be like here. Okay, roughly. Okay, and then we want to go at a distance of 4. So maybe be like right around here. Okay, so again, theta, this would be negative pi over 4 between the x-axis and that dashed line in the xy plane. Okay, this would be phi, which would be pi over 3. So starting the positive z-axis and going towards that dashed line that we drew in the xy plane, angle of pi over 3. Maybe the one that I drew might look even a little bit more like pi over 4-ish. Okay, so maybe a little bit further towards the xy axis than I did. And then just, you have to go to 4 units. Okay, so there'd be our point. Okay. So we're in that, we're above the xy plane, so a positive z. Here, in fact, z here would be positive. X would be positive, and y would be negative, right? Okay. All right, so using your conversions, and I'm going to just erase this dashed line here so I have some room to work. And I feel like switching colors too. Let's do that. Okay, so X would be, again, rho sine phi cosine theta. So we're going to have 4 sine pi over 3 cosine negative pi over 4. So that would be 4. The sine of pi over 3 is 1/2. No, it's not. The sine of pi over 3, I gotta think for a second because I'm thinking about trying to get it right in my brain here. If sine of pi over 3 would be square root. No, it is 1. No, square root 3 over 2. I'm picturing it wrong. And then the cosine of negative pi over 4 would be square root of 2 over 2. Okay, so then we'll get 4 square root of 6 over 4, which is square root 6. Okay. For y, and I'm going to erase what I have down here too. Y, we want rho sine phi cosine theta, or sine theta. So we're going to start out the same. 4 sine pi over 3 sine negative pi over 4. So we're going to get the same thing but negative, right? So 4 square root of 3 over 2 negative square root of 2 over 2. That's going to give us negative square root of 6. Okay? And then z will be your rho cosine theta. So that's going to be 4 cosine of, or sorry, it's cosine phi. I have it written down in my notes wrong. 4 cosine phi. So 4 times the cosine of pi over 3. Okay, so 4 times 1/2, which is 2. Okay, so in rectangular, it would be root 6, negative root 6, 2. Okay. All right, the second example, it's in rectangular, so we are going to go to, let's do green. X is going to be the square root of 3. Y is going to be negative 1. Okay, and then Z is going to be 2 root 3. Okay. So let's do our conversions here. Rho squared is x squared plus y squared plus z squared. So rho will be the square root of x squared plus y squared plus z squared. And remember, it's always positive. So we'll have the square root of x squared would be 3, y squared would be 1, and z squared would be 4 times 3, so 12. Okay, works out nice. Square root of 16, which is 4. Theta will be the inverse tangent of y over x. So we'll have the inverse tangent of negative 1 over root 3, which you know better is root 3 over 3. Oh, negative. Okay, so our angle, and remember, theta has between 0 and 2 pi. Okay, so if we're on the unit circle and tangent is negative square root of 3 over 3, you actually, there's two possibilities, right? Okay, so it could be in your second quadrant, it would be 5 pi over 6. Or if we're in the fourth quadrant, it would be 11 pi over 6, right? Okay, well, if you think about that one a little bit, look at where we are in the xy plane. We're in the fourth quadrant. So we would have 11 pi over 6. Okay. And then phi is going to be the inverse cosine of z over rho. And you've already found rho. Okay, so it's the inverse cosine of 2 root 3 over 4. Okay, or the inverse cosine of root 3 over 2. Okay, so what angle has a cosine of square root of 3 over 2? That is going to be pi over 6. Okay, so in spherical, we'll have rho, theta, phi. Okay. All right, let's get into some more of these then. Thinking about what some of these graphs are going to look like. Okay, so the first thing that we want to think about is if any of these things are constant. Okay, so if rho is a constant, theta is a constant, or phi is a constant, think about what's going to happen. Okay, so let's draw rho equals 3. Let's draw theta equals pi over 3. And let's draw phi equals pi over 4. Okay? Okay, so if these are constants. Now, if rho is a constant, okay, that means that your distance from the origin is always 3. Okay, so that is going to be a sphere with radius 3. That's going to be a little bit tough to draw, but I'm going to do my best. Okay, centered at 0, 0. So going out to 3 in all directions, including above and below. Okay, roughly. All right. Okay, theta equals pi over 3. So my angle here is pi over 3. Okay, so what that means too is that we just have it's actually a half plane because there's no way for us to get to the other side. Like rho is going to get us up and down. Phi, remember, is measured from the positive z-axis. So this is going to be actually a half plane. Okay, so you can think about the plane that goes on and on to the right. Okay, because if you think about it, in order for us to get to the other side there, phi would have to be negative, which can't happen. I'm sorry, rho would have to be negative, which can't happen. Or phi would have to be outside of the bounds 0 to pi over 2. Okay, so this is a half plane. Okay. All right, now phi equals pi over 4. So that means that we are always a distance of pi over 4 from the z-axis. Okay, all the way around. So this is an interesting one. This is a cone. Okay. And it has the vertex of the cone at the origin. It would go on forever too. Okay. And then that angle along the side would be like a 1-to-1 angle there. Okay. So let's make sure we can kind of visualize those. Okay. And that those constants make sense. Let's do a little bit more complex graphs here. We have rho equals 2 cosine phi. Okay, and I think this one, it wants you to describe it and convert it. Okay. So first of all, we can kind of think about this a little bit because it only has 2 variables here. So you can think about like if different values of phi. Okay, if phi is 0, then rho is going to be 2. If phi is like pi over 4, rho is going to be 2 times square root of 2 over 2, so square root of 2. I guess I could have done pi over 6 first. Okay, the cosine of pi over 6 is square root of 3 over 2. So then we have square root of 3. Pi over 3. Right, cosine of pi over 3 is 1/2, so we just have 1. And pi over 2. Rho would actually be 0 again. Cosine of pi over 2 is 0. Okay, so if we kind of start to draw these a little bit, if phi is 0, rho is 2. Okay, if phi is pi over 4, rho is the square root of 2. So we can think about like if we're at pi over 4, okay, anywhere, let's kind of think about your cone again, right? So anywhere along there, we are at a row of square root of 2. So go out here, distance of square root of 2. Okay, and then just rotate it around. Okay. I should have done pi over 6 first. Pi over 6. Okay. We'd want to go out a distance of square root of 3. Maybe that's even a little bit better on the first one I have is more like that. Okay, so at pi over 6, we'd go out square root of 3. Rotate it around. Pi over 4, we go out square root of 2. Rotate it around. Sorry. Pi over 3, we would go out a distance of 1. Rotate it around. Okay. And then pi over 2, we're back to 0. I didn't do a great job drawing that. And I apologize. But what that ends up being is a sphere. Okay. And it is, excuse me. This ends up being a sphere. And it's actually centered at 0, 0, 1. Okay. And the diameter is 2. Okay. So it's similar to if you remember when you did your polar graphs, r equals 2 cosine theta. If you remember, that was a circle. with a diameter of 2. Okay, so this is a sphere with a diameter of 2. Okay. All right. And we can also convert it. Okay. We've got the rho equals 2 cosine theta, or phi, I'm sorry. Your little trick here is to multiply both sides by rho. So we'd have rho squared equals 2 rho cosine phi. So x squared plus y squared plus z squared equals 2z. See how fun that is, right? Okay, so x squared plus y squared plus z squared minus 2z equals 0. Complete your square. And we'd have a 1 on that side. Okay, so again, that is a sphere centered at 0, 0, 1 with a radius of 1. Okay. All right. Then another example, they give us one that's in rectangular. I think this is example 10 maybe in the book. X squared minus 2x plus y squared plus z squared equals 0. Okay, and that's a sphere again, similar to what we just had, right? You can complete the square and the x's and get that sphere. Okay. Well, we have an x squared and a y squared and a z squared. Okay, so that's a rho squared minus 2, and x, remember, is rho sine phi cosine theta. Okay, so that's it. That's all you got to do. Okay. We can do another example here. We're going to sketch, and then we'll get into the integrals here in a second. We're going to sketch the region described by rho is between 1 and 2. Okay. Phi is between 0 and pi over 2. And theta is between pi over 2 and 3 pi over 2. Okay, so now if we kind of think about each of these separately, rho being between 1 and 2 means that it's like a sphere with a hollow center. Okay, just like if it was r is between 1 and 2, you have like that ring. Rho between 1 and 2, you're going to have that three-dimensional, so it's going to be like a sphere. Okay, but hollow in the middle. Phi being between 0 and pi over 2. So from the positive z-axis, I go an angle between 0 and pi over 2. That means that I have all positive z values. Okay, I'm above the xy plane. So putting those two together, it's a hollowed out sphere, but only the top half of it, the top hemisphere. Okay, and then here, theta being between pi over 2 and 3 pi over 2 tells me I'm only in quadrants 2 and 4. I'm sorry, 2 and 3. Okay, so if I try to sketch this out, I'm going to get kind of like a little better of an angle here at it. X, Y, Z. 1, 2, 1, 2, 1, 2. Okay, and then we would only be in quadrants 2 and 3. Okay, so what this might look like, oof, this is going to be a tricky one here. This would be 1, 2. Okay, and then they'd be like, oh, doing okay there. Cheating a little bit because I do have a little bit of a sketch on my paper. Okay, kind of picture that. This is coming around the back here, and then I'm even going to use a different color here. This would be like the cross section. like that, almost like a cave. Okay. All right, let's get to these integrals then. So I'm going to do my best to draw a nice sketch here. So much like with with the cylindrical, that region can best be described in polar coordinates, but also then you have to think about your z's would make more sense being like curved surfaces, I guess. So let me get this here, x, y, z. We're going to have a shape. Oof. Okay, maybe that makes, let me get that one edge that's a little bit off there fixed. Okay. All right, and then we're going to kind of like think about projecting these corners down. As best I can, which is not easy to do. Here, I'm not going to do a great job here. They're going to be like in a wedge here. Okay, where like you got the back edge and the front edges. Okay. In fact, I'm going to erase those lines just so that they don't get in the way of the other stuff that we're going to draw here. Okay, but you can kind of think about that being projected down. Okay, into the XY plane. Let's do that. Okay. So there we go. We would have, this is, let's do the thetas first. Okay, so we would have theta is between alpha and beta. So there would be alpha. There would be beta. Okay, and then our distance here, that would be delta theta. Okay. Then we're going to have our, let's see here, let's do our phis. Okay, so we will have 1 phi, 2 phis. Okay, so this would be phi. We're going to do phi between C and D. I honestly don't know why they don't use Greek ones for this. Maybe they're running out of letters. Okay, but C and then D. Okay, which then makes this distance here delta phi. Okay, the difference in those angles. Okay, and then finally, we're going to have rho between A and B. Okay, so rho would be, here I'm going to do, this is the distance of A, and then this is the distance of B. Okay, measured from the origin. I just don't want to draw more lines over the ones that I already have. Okay, which would make, and actually, this should be going to the front. Okay, so then that would make this side length delta rho. Okay, so yeah, this is supposed to be more like at A I think I got it slanted a little bit wrong where I wanted it, but there we go. Okay, so I'm going to kind of draw another little figure over here. Well, first of all, though, remember that this distance out would be rho sine phi. Okay. That isn't measured from the origin, just in the xy plane. Okay, so again, now if I take my little figure that I tried my best to draw, okay, this side here would be delta rho. Okay, this side here, okay, we need to think about, and then we also want to think about this side here. Okay, this side here is like this outer edge here. Okay, so it's the same length as right here. Okay, it's a sector of a circle, right? So it would be beta minus alpha out of 2 pi, okay, times the radius of that circle, which, I'm sorry, times the circumference of the circle, which would be 2 pi rho sine phi. Okay, that's just your arc length, right, of a sector of a circle. The portion of the circle would be the angle b minus a out of 2 pi. The circumference would be 2 pi r. Okay, we can do something similar for this piece right here, which kind of goes along with this curve over here. So again, that would be the difference in the angles. So that would be d minus c out of 2 pi times 2 pi r. Well, it's just rho there. Okay, so the entire volume would be delta rho. These 2 pi's will cancel out. These 2 pi's will cancel out. Okay, so then we would have d minus c times rho. And then we would also have beta minus alpha times rho sine phi. Okay, well, d minus c, remember, that's just delta phi. And beta minus alpha, that's just delta theta. Okay, so what we're left with here is we have a rho squared sine phi. And then we have our delta rho, delta phi, delta theta. Okay, so that'd be the volume of one of these little like wedge pieces. Okay, so just like all the other times that we've done integrals, we got to think about having these infinite wedge pieces. Okay, all right, so, and we're going to call this region E. Okay, such that that's true about E. Okay, so let's put this all together. Our triple integral over E of a function in x, y, z dv, okay, will be our limit as, delta rho goes to 0. Delta theta goes to 0. Delta phi goes to 0 of our summation. And we're going to keep it in rectangular first. I equals 1 to L. J equals 1 to M. K equals 1 to N of F of X star I, Y star J, Z star K. IJK. Sorry, we got to get all of them, not just the Z's. Whatever. Okay. And then delta V IJK. Okay. Now let's switch those to polar. So that's your limit again. And I know that these proofs can get a little bit much, but you're never going to have to regurgitate them. It's just kind of a basic understanding if you can get it. It doesn't help that my Chromebook is so slow. Okay, summation I equals 1 to L, J equals 1 to M, K equals 1 to N, the function. Okay, so then X is rho I sine phi K cosine theta J. Okay, and I'm not sure why they choose the subscripts that they do. Instead of using asterisks for whatever reason, they use tildes. Okay, and then Y would be rho sine phi sine theta, tildes. Okay, and then remember Z is just rho cosine theta. And we're not even done with that yet, because then the delta V has to be the rho squared sine phi delta rho delta theta delta phi. Whew, all that. Okay, and again, the important part is that now we just get the correct integral. Integral from C to D, alpha to beta, A to B, whatever your function is in terms of rho sine phi cosine theta, rho sine phi sine theta, rho cosine phi. I don't know why. This should be phi too up here. My notes, I kept writing the wrong thing. Okay. And then we need that rho squared, just like in polar, how you always had that R there. Now we also have a rho squared sine phi there. Okay, and then d rho, d theta, d phi. Whew, okay, and again, you can reverse the order however you need to make it work. Okay. All right, we're going to get some examples with integrals, and then we'll be done. So try some of the integrals as we do them, for sure. All right, and I might at some point have to stop if this gets too slow and just make a second video, but we'll try it. Example, I think this is number 18 in your book. It asks us to sketch and evaluate. Okay, so we have the integral from 0 to 2 pi, integral from pi over 2 to pi, integral from 1 to 2, rho squared sine phi. Okay, which means that we're just integrating one, so we're just finding a volume. D rho, d phi, d theta. Okay, now the integral is not the tough part here, right? We can do that pretty easily. We'll do this integral just so you have one to look at. I won't do them all again. Just like the previous video, I'll tell you the final answer. So first, integrate with respect to rho. Okay, so of rho cubed over 3. And this is actually one too where you can, now that I look at it, I'm going to stop for a second, because remember, we can split these up. If they're separable, we can separate them. Okay, so this is a strategy that maybe we haven't used for a while, but we can easily separate this into our integral from 0 to 2 pi of just d theta. Sorry, this should be a rho here. Okay, times your integral from pi over 2 to pi. That was d phi, but there's a sine phi there. times your integral from 1 to 2 of rho squared d rho. Okay, now you definitely don't have to switch it like that. You know, I would encourage you to try it both ways and just see that it's going to be the same. But this kind of makes your work a little bit easier, right? Because this would be then theta from 0 to 2 pi times negative cosine phi from pi over 2 to pi times rho cubed over 3 from 1 to 2. Okay, so then we'll have 2 pi times negative cosine of pi minus a negative cosine of pi over 2 times 8 over 3 minus 1 over 3. Okay, so that means that we'll have 2 pi times negative cosine of pi. So cosine pi is negative 1, so it'd be 1. Cosine pi over 2 is 0. Then we have 7/3. So we've got 14 pi over 3. Okay, let's sketch it though. That's the fun part, right? I'm going to get a not such a fat pen here, just a second. Look at that. Okay, so theta will be between 0, that's much better, between 0 and 2 pi. Phi is between pi over 2 and pi. And rho is between 1 and 2. Okay, so again, this tells me that we've got these spheres, concentric spheres, okay, all the way around. So all 4 spheres, let's do that, all 4 quadrants. Okay, and then again, the fact that phi is between pi over 2 and pi, that means that I have only negative zeros, or negative z's. Okay, so what I'm going to have here is concentric spheres centered at the origin between 1 and 2, going around the whole way, but only the bottom half. Okay, so this would look roughly like okay, kind of like that. All right, where this is between 1 and 2. Okay. All right. Next example. And this is number 20 in your book. I think this one must give you a diagram. Let me take a look quick in the book. Yes, they do. Okay, so example 20 in the book, now they give you a diagram and they have you set up the integral. Okay, so the diagram that's given it's kind of like this. Hopefully you can kind of see it. Let's see, some shading back there, some shading along the edges maybe here. You can see what's going on. Okay, so, and this is from 1 to 2. So we've seen this a couple times now, right? We've got the rho between 1 and 2. Okay, z is always positive, so phi must be between 0 and pi over 2. Okay, and then we're only in the second, third, and fourth quadrants. Okay, so theta must be between pi over 2 and 2 pi. Okay, so there you go. That's it. By looking at they give you just the diagram and ask you to set up the integral that would give you the volume. So our integral then, does it just say the volume? Or just some arbitrary function, it says. Okay, so we would have that arbitrary function here. I'm going to go to the next line just so I have enough room because these take so much room. So 0 to pi over 2 for phi, pi over 2 to 2 pi for theta, 1 to 2 for rho. Again, it doesn't matter what order you write those in as long as you're consistent then on the back end, right? Function in terms of x, so that would be rho sine phi cosine theta, okay? And then y, so rho sine phi sine theta, and then z, so rho cosine phi, and then rho squared sine phi. And I've got my rows on the inside, so d rho, d theta, d phi. I didn't mean to make a double d here. Oof, this is getting bad. Okay, there you go. Okay. All right, we'll do a couple more examples. There's not much left here. We're going to do another one, though. Example 22 in your book. It says, exercise 22, evaluate the triple integral over h of 9 minus x squared minus y squared dv. And they tell you that h is a solid hemisphere. Okay. Solid hemisphere, x squared plus y squared plus z squared is less than or equal to 9, and z is greater than or equal to 0. Okay, so we've been looking at some hemispheres quite a bit here, right? It's solid, there's no hole in the middle, so we just have that rho is less than or equal to 3, be greater than or equal to 0. Okay, it says it's the entire hemisphere, so it goes all the way around, so theta is between 0 and 2 pi. And since z is positive, phi is between 0 and pi over 2. Okay. Now we also need to change our graph here. Our function. It's rectangular right now. Okay. So we need to switch that over. This would be 9 minus rho. So x, remember, would be rho sine phi cosine theta squared minus rho sine phi sine theta squared. Okay, so 9 minus, we can factor out a rho squared sine squared phi. And then we're left with cosine squared theta plus sine squared. Okay, because of that double negative there, which is just 1, right? So then we have 9 minus rho squared sine squared phi. Okay, pretty handy. Okay, so then when we set it all up, again, since all of our limits are constants, it doesn't really matter what order we do them in, and maybe we'll decide that we want to switch them around. Okay, and that's fine. But we'll start with just, I'm just going to do 0 to 3, just the order that I have it written, 0 to 2 pi, and 0 to pi over 2. Then my function is 9 minus rho squared sine squared phi. Okay, don't forget your rho squared sine phi. Okay, and then I've got my pi over 2, so I've got d phi. And then I've got my 0 to 2 pi, so d theta, and then d rho. Okay, So you're ready to integrate, right? And you can look right away and see that I probably don't have it in the best order yet, right? I don't want to integrate that sine cubed phi to the fourth or whatever. So I probably want to switch it around here. If I expand these out, I'm going to have 9, let's see, rho squared sine phi minus rho to the fourth sine cubed phi. Okay, integrating sine cubed, I guess eventually I'm going to have to do it. Okay, but maybe I want to do it last once I've gotten rid of some other things. So I think the way that I ended up doing it in my work is I integrated with respect to rho first, actually. Okay, and then I did phi, and then I did theta. Okay, so go ahead and try it yourself. Okay, see where you can get with this. You should get an answer of 486 pi over 5. So definitely, stop right now and just try this. But here's a hint for you. Remember, when you integrate sine cubed, okay, you have to use one of your trig identities. Okay, and then you would make u equal cosine theta and du equal negative sine theta d theta. So that's your little trick for when you're integrating a sine or cosine with an odd power, that you have to do that u sub. Use that identity and do the u sub. Okay, so once you have to integrate that sine cubed, at some point you're going to have to do that. Okay, you can definitely split this up into 2 separate integrals. Your first term and your second term. That first guy is going to be pretty easy to do. It's that second guy that when you get to the integrating the sine cubed, and there's no way around it, you're going to have to do it. You're going to have to use that trig identity. Okay, so go ahead and give it a shot. Make sure that we can get that answer. Okay, one last little one here that comes up, and we saw it when we did the cylindrical. This is exercise 32. Okay, just remember, I guess this one's a little tricky. We want to find the mass and the center of mass of a solid hemisphere with radius A. Okay, with density proportional to the distance from the base. Okay, so I guess I'll help you get this one set up a little bit. Okay, but remember, when we're doing mass, we integrate your density function. Hold on. Okay, then when you do your moment around xy, you integrate z times the density. It's being so slow. Moment around xz, you integrate y times the density. Moment around yz, we integrate x times the density. And then x bar is moment around yz over mass. Y bar is moment around xz over mass. And z bar is moment around xy over mass. Okay, so just like that's your basics there, right? We can get a little bit more formal than that, but that's the basic idea. Okay, so first of all, a solid hemisphere with a radius a. So that is again going to have rho is between 0 and a. Theta would be between 0 and 2 pi. And since it's a hemisphere, we would have phi between 0 and pi over 2. Okay. The density is proportional to the distance from the base. So if we have a hemisphere, the distance any point is from the base would be at z coordinate. Okay. So rho is proportional to z, which would be proportional to rho cosine. Oh, I'm not going to use rho for that. I just realized that would be a bad idea. Rho cosine phi. I'm just going to use a capital D for density. Man, good thing we're almost done. This is getting super slow. Okay, so that was a little tricky. We have to get that density equation. Okay, so for your mass, you're going to integrate k rho cosine phi. And don't forget then your rho squared sine phi. And then you've got to do your, d phi, or d rho, d phi, d theta, right? And phi is between 0 and a. Phi is between 0 and pi over 2. And theta is between 0 and 2 pi. Okay, so that's going to get you your mass. Okay, so go ahead and do that. And make sure that you can get the final answer is k a to the 4th pi over 4. Okay, and then go ahead and do the rest of the work here. Just make sure that, when you use density, that should be k rho cosine phi. And then your x, y, and z, make sure you swap out your polars. Okay, use your conversions. X is rho cosine theta sine phi. Y is rho cosine theta. I'm sorry, rho sine. What did I just got it mixed up, didn't I? X is rho. Let's see, it's going to be cosine sine phi cosine theta. Y is rho sine phi sine theta. And z is rho cosine phi. Okay. And then just make sure you don't forget your rho squared sine phi d rho d theta, or sorry, d phi d theta when you do your integrals. Okay. The bounds will be the same. All right. So I'm going to leave that to you to try on your own. I just wanted to make sure that you understood the, this piece of it. Once we get the integral set up, the integration's kind of just on you. Okay. So I can definitely, if you're trying these and you're not getting them, just let me know. I would be more than happy to make a video where I go through these integrals too. I don't mind at all. I just don't want to get these videos to be too long. Okay. So once you're all done with this, you guys, if you get x bar, y bar, z bar equal to 0, 0, 8a over 15, then give yourself a big pat on the back because that's it. And that's kind of a beast of a problem and you got it. Okay. All right. We're going to stop there and we will see you in class.